Hello and welcome to this video about math. In this video we'll prove that a certain polynomial that we can make up from the eigenvalues can get the square root of non-diagonalizable matrices. So since any matrix is Jordanizable, then we only need to prove this theorem for Jordan canonical matrices, and there's no need to test it for conjugated Jordan canonical matrices, since if it works for any Jordan canonical matrix, then it will work for their conjugates. In fact, we only need to prove it for a matrix that's one giant Jordan block like this one. So this is the square of a Jordan block matrix, and you can see the square of the polynomial x plus 1 embedded in it. And this is a cubed, and you can see the cube of the polynomial x plus 1 embedded in it. So we don't need to show the whole matrices for the next powers of a. We only need to show the first row, and it is repeated in the matrices that we'll get for greater powers of a. These all have the polynomials of x plus 1 raised to the power of a positive whole number in their first row. So now to more formally prove that each power of the matrix A contains the polynomial x plus 1 raised to the power of n, we'll prove it using induction. We'll start with these matrices. A is the Jordan canonical matrix with eigenvalue of x, and that is one giant Jordan block. B is raised to the power of n, and we'll assume that B contains x plus 1 to the power of n in its rows like this. We can write them out in combinatorics notation like this. So we'll set C to be the next power of A, which is a to the power of n plus 1. Then C will be B multiplied by A, like this. We can write it out using just the first two rows, and we'll convert all of the entries into combinatorics notation that aren't 0. Then we can convert all of the numbers in this matrix into combinatorics notation. After the multiplication, we'll get this lot of entries which needs simplification. We can gather terms into the brackets like this. And we can use Pascal's triangle formula to simplify these entries to become these entries, with the top number raised from n to n plus 1. But we still have to work on the end entries, Cnn and Cn0. And this is easy because these entries are all equal to 1 and can be set to be the next entries using this rule. So now to prove this result more formally, we'll write each entry by this row and column subscript notation. This is what the entries are for matrices A and B, where B is a to the power of n. And this is what they should be for C. We'll prove this result for C using this notation, where C is a raised to the power of n plus 1. So now to prove this particular result, we'll start with this statement, which is gotten by multiplying A by B. This entry is the sum of these two entries. One of the entries is multiplied by x. We'll substitute what the entries are here, and they are combinatorics multiplied by powers of x. And then we'll simplify the powers of x. We'll factor out the x. And we can use Pascal's triangle to give us this value which proves this first part of the theorem, which we'll need to evaluate the second part. So this is what the square root of this Jordan canonical matrix with one giant Jordan block is. We'll need to use this to solve the next part of this proof. So we'll apply this polynomial that we want to find to the matrix A, which is a Jordan canonical matrix, and we can substitute the identity matrix for A raised to the power of 0. So we'll expand this polynomial out for a 4x4 matrix to look at this polynomial more closely. We'll colour all of the first elements of these matrices red and circle them because we want to make them into an equation by themselves. We'll do a similar thing with all of the other elements in the first row. And so this is what all of these equations are after gathering the entries in the same positions together. I've decided to keep them in the same colours as they were in the matrix equation. Then we can pack all of these equations up into this matrix equation. We can multiply each row by the corresponding factorials so as to simplify the vector on the right. So now it's only the derivatives of the square root functions, including the square root function itself. We can simplify this matrix. We can also write in all the other factorials like 0 and 1 factorial so as to get a better look at the structure of this matrix. So we'll set F to be equal to this matrix. And this is what each element in this matrix is equal to. We'll prove it later in this video. So we'll write out this matrix using combinatorics notation. And F is equal to this matrix. And we can more easily see that this is what each element of matrix F is equal to. So I'll just show you again how I set these equations up from these matrices in a slightly different way. This is how I set up the first equation. And this is the second equation. It contains 1 0. This is the third equation, and it contains 2 zeros and is simpler. And this is the last equation, containing mostly zeros, and the last coefficient is equal to the last entry of the top row. So I'll just show you how to get the first equation from these matrices in combinatorics notation. So now to prove that this entry of matrix F is equal to this, using all of the powers of matrices that we've already used to represent the different powers of Jordan canonical matrices. We'll let A to the power of n be equal to the Jordan canonical matrix raised to a particular power of n. And this will be the ijth entry of this matrix. I put the n inside the brackets so that it won't be confused with raising the entry to the power of n. So this is what this entry will be. It will be a function of its row and column positions. But we'll only be using the first row, so we'll set I to be 1 here. We'll set this entry of matrix F to be equal to the entry that we're trying to find for this matrix. And this is what it will be in terms of the powers of matrix A. We'll substitute the variables in here like this. And so we'll expand it out for the entry of A. We'll be substituting j minus 1 in for n and I for j. It is a bit confusing, but they're fairly easy to keep track of. And after some simplification, we'll obtain this value for the entry, and this completes the proof of the second part. So let's look at this matrix equation again. Each row in this matrix represents a polynomial, and each row is the derivative of the previous row. Now we have to prove that each row in the matrix is the derivative of the previous row. So we'll write this out more technically, that each entry is the derivative of the entry above it. So this is the entry that we're trying to find the derivative of. We'll expand out the combinatorics function. We'll simplify the first term in the denominator. Then we'll eliminate these two terms. Now we'll get the derivative of this expression. And these two terms cancel out to give this factorial. We can put in the factorial of I. We can place them in the numerator and denominator. We need to desimplify this expression this way so as to complete the proof, and can work backwards like this in a proof. Then we can take the top factorial of I out of the fraction. We can also desimplify this expression, getting ready to use an I plus 1 term. We can then simplify the fraction to give us this combinatorics term. We can also desimplify this factorial term. And so after differentiating this entry, we get the entry below it, so that completes this proof. So this completes the whole proof. So I hope that you found this video to be helpful, interesting and insightful. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts and ideas in the comments, and thanks a lot for watching.